exam number 1. This is in class Friday. Okay, so as far as this thing goes, you guys have, I posted some, couple of old exams you can take a look at. The body of material, I think, is exactly the same for what's on those ones. So anyway, where we're going is up through and including what we've done with unique factorization, I guess right up till this moment right now. Okay, so we're proving the fundamental theorem of arithmetic and maybe whatever we did last time. We're working with divisibility in GCDs from the perspective of prime factorization. So we'll end up at some point today maybe moving to the next thing. But anyway, just a couple of comments about this exam. Again, you can see the old exams, get a sense of what's on it, but it's a mixture of some things. Like there might be some more computational problems you solve, solve Diophantine equations, find GCDs, use the Euclidean algorithm, that kind of stuff. You may see a couple proof questions as well, like you'll see on those. What I guess I wanted to say, if it needs to be said, is that you are, of course, welcome to use the results from class, theorems we prove in class. This is the reason why we prove them, right? So that we can use them later and build upon them. So anyway, when you're solving problems, you are, of course, welcome to use the important theorems from class. You never need to know the reference or something. What I mean is, never say something like proposition 2.7 or something like that. Don't try to memorize that. But if you say like, since D is the GCD of A and B, we could write D in the form A times X plus B times Y for integers X and Y. Like that's using a theorem. It's fine. You can use it. Okay. There's probably some minor exceptions to what I just said. So you might see a question like on an exam that says something like, prove this thing without appealing to the fundamental theorem of arithmetic. So like you have to maybe give an argument that doesn't use the newer stuff we just discussed about prime factorizations. If that shows up, it's probably intended to be some kind of proof that could have been done in the previous chapter using facts about GCDs or something. Okay, so there might be one or two places like that. There might be a place where essentially you're asked to prove a theorem from class or something. You're not allowed to say we proved this in class, so I'm done. Okay, I hope that's kind of common sense. But, just to be clear. But otherwise, just again, don't be afraid. You are allowed to use the facts from class. Okay, do you have any questions or concerns about anything that I did? So, anyway, I wasn't going to say much more. We're not going to have like a full-blown review session or something. So we're going to move on. I want to do one exercise with you, which I guess could technically fall under the umbrella of feeling like a little review exercise. Because there's something, for whatever reason, I don't know if I forgot to do it or something, but there's a result in chapter 2 that, we didn't prove it in class, we just apparently glossed over it, but I wanted to revisit it. And its proof is a nice exercise in some of the things we learned. So anyway, this is just a bit of a leftover from chapter 2 that we just didn't talk about in class yet. And really where it belongs is kind of in this discussion of things you can prove after you learn about GCDs. Okay, so this is proposition 217. So the situation here is that you've got three integers, A, B, and C. And A and B are relatively prime to each other. And the situation here is that actually, both A and B divide C. So if A divides C and B divides C, then the conclusion here is, in fact, their product will divide C. So this is something I don't think we talked about in class. Let's just prove it. I mean, this is perhaps supposed to be an intuitive sounding thing, right? So I mean, especially now in light of prime factorization, we officially discussed that. But you know, A and B have no prime factors in common. They have no factors in common at all, right? So if they're both divisors of C, then since they have no sort of overlap in terms of common factors, like all the primes of A and all the primes of B should also divide C. And so you should get this whole product divide C. And so one thing you could do is, if you want, to try to stitch together an argument using what I just said, prime factorizations in the fundamental theorem of arithmetic. In the textbook, this showed up before that, so we don't need that to prove it. So let's do it using the older methods. I mean, the earlier methods from the course, just because it's a good place to use to practice with some of these things. So anyway, one of the key assumptions, though, is that the GCD of A and B is 1. Okay, and so it's often a good time. When you have an assumption like that, it's often useful to invoke this fact about how the GCD can be expressed as a linear combination of A and B. So we'll invoke that in a second, but maybe we'll start with these other assumptions. So since, what do we have? A divides C, and B divides C. What we can write is we can write C as A times something, let's say maybe E, but also C as B times F for some integers, E and F. And then, since the GCD of A and B is 1, we can invoke one of our big theorems. So there exist integers x and y. And such that 1 is equal to A times x plus B times y. Okay, and so we have to figure out what to do with all of this, how to combine it together in a clever way. Yeah.
I thought we could write like the GCD of A and B, even like if it wasn't 1, we could still write it as the x plus b 1. Is that true?
Yeah, of course. Yeah, it is true, but in this case it's 1. So.
Yeah.
Yeah. So right. So if the G, I mean, if this was a D, if we just said we'll call this D, then you could put a D here. That's the theorem. I don't think I ever said it. I don't know if the book says it, but by the way, this is sometimes called Bézou's theorem. Attach a fancy name to it. I believe that's the correct spelling. But that fact about GCDs and how you can write them as a linear combination of two integers, sometimes people call it that. We didn't call it that previously, though, so in case you're confused, I'm just dropping the name now. But anyway, so how are you going to combine this stuff together? I mean, we played a similar trick in a different argument in the past, but I mean, the end goal is to try to say C is divisible by something. So you do need an equation that says something of the form C is something. So we did a trick like this in the past, but it turns out to be a good idea here, actually, if you multiply both sides of this equation by C to say something useful about C on the left. Okay, so here's why it's going to work. And so multiplying by C gives C on the left, right? And then what you have is A times C times X plus B times C times Y. And if you think for a second, you might realize why this is going to work, because C is divisible by both A and B. So this C, I mean, it is divisible by B. So there's a factor of B here. So you actually have a factor of A times B sitting right there. And then this C, you'd say, well, it's divisible by A, so it has a factor of A in it. So you have a factor of A and B sitting right here. So both terms are going to have a factor of A times B. Okay, so then the way you would work that in is just plug these two equations in for the different C's. Just you can do the right one in the right place. But so, I mean, it would not be smart to plug in A times E in place of this C. That won't be useful. But C is equal to B times F. So this is A, B times F times X. And C is also equal to AE. So if you insert that here, That's useful. And because what you can do is factor an a times b out of this whole thing. And what remains if you factor ab out is fx plus e1. Okay, and because everything in sight is an integer, all the letters are integers, the expression fx plus ey is also an integer. So this shows what we wanted. Right, because it says c is ab times another integer. Okay, so anyway, I always thought this kind of an argument was like something that when you first see it, you might not think you would have ever thought of it yourself. So that's why we just show it to you a couple times, then you say, well, maybe one day you'll think of it, right? So, or think to try something like this. Okay, yeah, the other time we did a similar trick was, there was a different theorem that said something like, this was similar to, I think, a theorem that said, what was it? If GCD of A and B is 1, and you know A divides BC, then A divides C. This was an important fact we proved in class, but it was a similar flavor of argument. If you forgot how it went, you can just try to do it yourself. Okay, do you guys have any questions or comments on this? Yes?
Would the other direction be true as well?
The converse of,
Yeah.
of this one?
Yeah.
And what would that be?
So if A divides C and B divides C, then the GCD is 1. And then the...
Oh, wait. Yeah. There's a lot of assumptions here, right?
Yeah.
So I'm not sure exactly what we mean.
So basically, if AB divides C and A divides C and B divides C, then GCD is 1.
I don't think so. Unless it's something that's true for all C or something really strong. But I don't think so, because I think you could just come up with a C that has a bajillion prime factors in it, and then make an A and B that have some of those in common, and make this. I don't think so. I don't think so.
It's like 62 and 72.
Yeah, I mean, yeah, I don't think so. But yeah, okay. But yeah, exercise, trying to make an example of where it fails. It's always good to think about counterexamples and how things can fail. By the way, whenever there's like theorems like this that have like, an extra assumption thrown in, like, the GCD is 1, that's really important. Make sure you can come up with an example where the GCD is not 1, where this thing falls apart and it doesn't work anymore. That's good stuff to think about as a math person. Okay? Like, why was that necessary? Like, how would it break if it wasn't there? Okay. All right, anything else on this one? Okay, so I did want us to move onwards, but I mean, we proved the fundamental theorem of arithmetic, which is, a really important fact about numbers, and the uniqueness is really important, which is maybe something you take for granted or something. But the fact that prime factorizations is unique is a special fact. So what is going to happen in the next chunk of the course, the next chapter, is we're going to just use the fundamental theorem of arithmetic to just do a variety of other things, a hodgepodge of other things. This is going to be a chapter that's called Applications of Unique Factorization. So pretty much, I think, from section to section, it's just kind of all different stuff. The very beginning of this is a little bit amusing. The first thing we'll look at here, there's a little puzzle that comes to us in the form of a limerick, which I will write out for you. Slowly. Okay, so you guys know what a limerick is? Perhaps. It's a 5-line little poem that rhymes in a cute way. Anyway, let me lady named Chris, who when asked her age answered this: 2/3 of its square is a cube, I declare. Now what was the age of the miss? So here's the content right here. So her age, 2/3 of the square of her age is a cube, right? That is the only real information in this puzzle. Okay, and so we have to figure out what number has that property. How old is she? So now, so what is the assumption that's meant to be applied here? That is, where, as far as her age goes, it's an integer. Okay, so we'll just treat it as an integer. There's no halves or anything. So her age is an integer, and this little bit right here, just in case it's ambiguous, what is meant by this when we say it's a cube is we mean it's the cube of an integer, right? Like 8 is the cube of an integer, right? Because it's 2 cubed. Any number is the cube of something. Any real number is the cube of something, but not the cube of an integer necessarily. So anyway, let's ponder this a little bit and see if we can sort this out. I mean, there is in fact only one sensible answer to this question. Okay, even if it sounds like there might be multiple ones. I mean, what we'll see is there actually are multiple ages that could be the answer, but there's only one sensible one that could be the age of a human, I think. So we'll see how it works out, especially if it's a young lady. So the idea, though, is we're supposed to solve this by thinking about unique prime factorizations, right? So let's let A be her age. Okay, and so, A is an integer. It has a prime factorization. Okay, so A, we could do something like what we were doing a lot last time, which is write it as, 2 to a power times 3 to a power times, et cetera. Right, so let's say 2 to the, I'll call it A2, 3 to the A3, 5 to the A5, 7 to the A7. Okay, now, I mean, there are infinitely many primes, and there could be all kinds of stuff showing up in there, but let's write it like that. Now, we have to think about 2/3 of the square of this number. Okay, so 2/3 of its square is what, right? So 2/3 times A squared, and this is 2/3. Okay, now, I mean, when you square something like this, all the exponents get doubled, right? So 2 to the 2A2. 3 to the 2A3. Exponents get doubled across the board. Okay, and then, there's this 2/3 bit, right? Now, there's a factor of 2 here, so you can combine it into the power of 2. And it's also divided by a factor of 3, so that can get kind of taken into account into this 3. So what you actually have for this number is it should be 2 to the 2A2 plus 1, right? Because you pick up an extra 2, and then you lose a 3 because you're dividing by 3. So you have 3 to the 2A3 minus 1. But this 2/3 is not interacting with any of the other prime powers. Okay, so you have something like this. Now, this needs to be a cube, right? That is what the riddle says. So this is a cube. And again, that means of an integer. That's what we mean in the language here. Okay. So what does that imply, right? And so there's a little proposition which I think we can maybe just treat as a little exercise because I hope it's pretty clear. I mean, but something we just witnessed in this little bit of algebra is that, when you square a number and you're looking at prime factorizations, just all the exponents double, right? If you were to consider the cube of an integer, all the exponents would triple, all right? All the exponents would be multiples of 3, right, for a cube. And that's kind of the key point, actually, is if you have a number that's the cube of an integer, all of its prime exponents should be multiples of 3. Okay, and so let's just state this fact. Proposition 5.1 says, suppose k at least 2 is an integer. And let's let m be a positive integer. And the statement is, how do you know if m is a perfect kth power? So m is a kth power of an integer. This happens if and only if all exponents in the prime factorization of this integer m have to be multiples of k. Right, so this is something I think I'll just say, proof is an exercise. I hope it's pretty clear what it's saying and more or less why it's true, right? But so I mean, if k is 3, that means we're talking about third powers. That's what 3 means. It really means third. Okay, third power. So if k is 3, then we're saying that, you have something that's a cube if and only if all of its prime exponents are multiples of 3. Okay, in a perfect square, everything would be a multiple of 2. They would all be even exponents. Okay, so what we get then from this general fact in this situation is that if this thing really is a cube, then all these exponents sitting up top here are multiples of 3. Okay? So what does that tell us is the question, right? So let's see. So what we get is that all exponents, back to our riddle problem here, the exponents in that expression, so the 2a2 plus 1 and the 2a3 minus 1, okay, and the 2a5 and the 2a7, okay, and all the subsequent ones, these are all multiples of 3. Okay, and so there's two things we can do with this. One thing is just we can figure out a solution to this problem by just making some choices here to make these work out to be multiples of 3. Right? So I mean, it's pretty clear. If you want this to be a multiple of 3, one way to make it work, not the only way, but one way to make it work is just if a2 is 1. Right? That'll make this 3, and then that's great. So one possibility, okay, is that let's say a2 is 1, right? So that'll make this thing to be 3. How could you make this thing a multiple of 3? Well, okay, you can't have a3 be 0. That won't work. You can't have it be 1. That won't work either. I guess if it's 2, it'll work. Right? If a3 is 2, this is 4 minus 1, which is 3. Okay, so that would work. Now, for all of these to be multiples of 3, I mean, they could, well, what could work for A5 is, I mean, it could be 0, by the way. That's a good option. Otherwise, it would have to be something like 3, in which case the age is going to explode. If this has an exponent of 3, that's 125 sitting right there. So let's not go that far. But it could be 0, right? This could be 0, and 0 is a multiple of 3. So, oh, I'm sorry, this is supposed to be subscript 3. Sorry for that. That was coming from this one. But yeah, this is one possibility. You can just take all the higher ones to be 0, right? So a sub p is 0 for all p greater than or equal to 5. All right, that's one possibility. And so anyway, that's mostly gives you an answer to the riddle, which is pretty much the answer to the riddle. So the age then is going to be 2 to the first power times 3 to the second power, right, which is 2 times 9, which is 18, which sounds like the age of a young person. Okay, great. So it's checks out. You can take 2/3 of the square of that number and verify it's the cube of something on your own time, but it'll work. And so one answer to the question, and that's, I mean, maybe half of what we can do with this. The other half is to really think about what are the other possibilities. Are there any other reasonable possibilities that we glossed over? We just, came up with an easy enough looking way to arrange this at the end. But let's push a little harder and say what are all of the possibilities that we can have for these exponents. So let's consider other possibilities. Okay, so other possibilities. All right, so what do we have? I'll just write some of these things down. Right, so here's what we know. 3 divides 2a2 plus 1. We know 3 divides 2a3 minus 1. Okay, we know 3 divides, I'll write it just like this, 3 divides 2ap for all times p that are at least 5. Okay, so actually let's start with that last fact because that is the one that you could say something pretty quick about what's happening. Okay, so for this last fact, here's where we could apply something we learned, which is that this number 3 is a prime. Okay, if you have a prime that divides a product of 2 integers, we proved it has to divide one of the 2 integers. Okay, so 3 does not in fact divide 2. So it would follow that 3 would have to be a divisor of AP in this situation. Okay, so since 3 divides 2 times AP, what we get, well, let's say you follow this. And 3 divides AP. Okay, and so there's, let me just say, I don't know, there's a couple ways you can reason this out, but it's not, let's just point this fact out though. Right, so 3 divides that product, but it has no factors in common with the factor 2, so it has to divide the other thing. Okay. So that tells us exactly what's going on with all these other exponents. They're just straight up multiples of 3. Okay, so what we could say, let's write something this way. So a sub p has to be a multiple of 3. So we could write it like that using some other integer. So this is going to be part of our story, is that a sub p has to be a multiple of 3. Now, what about the other ones? The other ones are a little harder to identify exactly what's happening. We can figure it out if we do something. We're mildly under-equipped to handle this. What these things really are about, by the way, and this is looking to the future, these sorts of statements are actually best understood in the language of congruences mod 3. And we'll talk a lot, an awful lot in this course, in fact, about congruences mod n, say. Okay, and when we're more comfortable in that language, then we probably have a better way to process this. But let me still walk through this. So, I mean, if you know, right, so if you know 2a2 plus 1 is a multiple of 3, what does this actually tell you about a2? So let's see what we can get out of this. Okay, so we know this is the case. Okay, what this just implies by definition is that 2a2 plus 1 is 3 times, let's just say, we'll call it k2. All right, now, one of the issues with this equation is, what we really want to do is solve it for a2. Okay, that's what you'd like to do, is solve it for a2. If you solve this equation for a2, it looks a bit problematic, like if you just algebraically do it, because you have to divide by 2, and then it looks like you maybe have something that's not an integer on your hands. So we need to be a little bit careful about this. And so there is a notable observation that'll help clean up our algebra for us, which is this. So the left-hand side of this equation is an odd number, right? So an odd number always looks like 2 times an integer plus 1. So it's 1 more than an even, that makes it odd. So this is odd. What's on the right is 3 times something else. Okay, so what must be true, in fact, is that this K2 has to also be odd. Right? If K2 was even, that would contradict this equation. Okay, so here's just a little very mildly clever thing to note, is that K2 has to be odd in this equation right here. So let's just note this implies K2 is odd. So what that means, an odd number is one you could write as a multiple of 2 plus 1. So we'll write it that way. So we can write K2 in the form, what I'm going to call 2m2 plus 1 for some integer m2. Okay, and this will actually just help our algebra a little bit. So what we can do then is this. So we can solve for A2, first of all. So let's solve for A2. So if you algebraically solve this equation for A2, then you get 3 times K2 minus 1 over 2. And this was what I was trying to say looks problematic. Like it doesn't look like an integer necessarily. But since we know K2 is odd, if we insert this into here, it'll actually get cleaned up a bit. So what this would look like is K2 is 2 times something plus 1. Okay, if you clean this up, this says we have 6m2 plus 3 minus 1. And the numerator would be plus 3 minus 1. That's over 2. So what this actually tells you then is something notable, because now you can divide by 2, and it says we have 3m2 plus 1. Okay. So what this is telling us is that whatever this exponent a2 is, it has to be 1 more than a multiple of 3. Okay, now that was our first example. We picked something that was indeed 1 more than a multiple of 3. But anything that's 1 more than a multiple of 3 would be acceptable here. And that's exactly the possibilities for A2. Okay. So we can do something similar to sort out, to try to understand what is happening with A3, which is satisfy something similar but with a minus. So let's just see how this plays out. So in a somewhat similar fashion, right? We know that 3 divides 2a3 minus 1, and this implies 2a3 minus 1 is 3 times something that I'll just call k3 right now. And again, you want to solve for a3 like we solve for a2, but you'll have something that's a bit messy. But just as in the other argument, the left-hand side is odd, right? So therefore, the right-hand side has to be odd. Right? This is odd. So K3 must be odd. Okay, and let's say, like we did before, let's just say we write K3 as twice an integer plus 1. Like we did over here for some m3. Okay, and then we could just do the same kind of algebra. So we could solve for A3. So A3 is 3 times K3 plus 1 divided by 2. Right, and now if we insert this version of K3 into here, right, we get, in this case, 6m3 plus 4 over 2. Okay, so that'll look like 3m3 plus 2. Okay, so what we're getting here is that the kind of A3s we're allowed to have, they all have to be 2 more than a multiple of 3. Okay, like the number 2 is a great example of is we have fully used this information right here, this box of information, that all these exponents are multiples of 3, and we took that information and used it to say something notable about each exponent. These ones are just 3 times, they are actual multiples of 3. And then these ones over here are 1 more than a multiple of 3, and these ones are 2 more than a multiple of 3. So we could put it all together and say what other ages could she possibly have had. What I guess is true, by the way, let me just go back and take note of this. I just want to point out that that could not have been negative. It could be 0, but it can't be negative. Same is true about these, by the way. So for some, right, so of course that can't be negative because that would give you a negative exponent for A2, which isn't allowed. But having it be 0 is fine because that was what we had in our first answer. Same with this one. So the way this all worked out is all of our m's are all non-negative integers. Okay, so what we have then for A is we have 2 to the A2, 3 to the A3, 5 to the A5, 7 to the A7, etc. Okay, but now we said something useful about every one of these exponents. So the A2 looks like 3 times m2 plus 1, and A3 looks like 3 times an m2 plus 2. This looks like 3m, sorry, it's not m2, it's m3. This is m5. Okay, so what you would want to do with this then is separate these oddball plus 1 and plus 2 to the side. So we have, let me set aside 2 to the 1 and 3 squared. And then what's left is 2 to the 3m2, 3 to the 3m3, 5 to the 3m5, 7 to the 3m7, like that. Okay, and 2 things. First of all, this is 18. That was our answer from before. Okay, now what's going on with this thing is it is a prime factorization in which all the exponents are multiples of 3. That makes it a cube. Okay, but what you could do is you could write it like this. To the 3rd power. Okay, that whole thing to the 3rd power. And this thing right here is just an arbitrary integer. Let's just call it, say, capital M. Okay, so that's an arbitrary positive integer. It could be 1, by the way, if all the m's are 0, but otherwise it's just a positive integer. And so what we have is 8 times the cube of that positive integer. Okay, so what happens is okay, so here's your complete solution set for this problem, is that there's more than one answer. But the other answers have this form, right? So they all look like 18 times the cube of an integer, positive integer. Okay, the smallest positive integer is 1. If you plug it in equals 1, that's our answer from earlier. So the next smallest possible age for this person would be when m is 2. Okay, and then when m is 2, that's 18 times 2 cubed, which is already a pretty big number, right? It's 18 times 8, which it's quite a challenge to figure out what it is. So let's stare at this. Oh yeah, it's 144. Okay, so the next smallest age is awfully large, in fact. Okay, so anyway, we just point this out. Right? M equals 1 gives us our answer from earlier. But if m is 2, right, you get 18 times 2 cubed, which works out to be 144, which is probably not the age of this young person. So that's the next smallest possibility. And if you really wanted to say, no, you realize these are going to get out of hand, that would be 18 times 27, I think that's a big number. It's 486. Okay, so that's the thing that totally justifies that the answer to this riddle must have been 18. Right? It couldn't be anything else. Okay, but anyway, the last part was maybe the more interesting part, and just finding one answer. Does that make sense? Is that okay? Yeah, again, later, we're going to, this may have felt a little awkward now, and again, we'll have more language and tools for dealing with these kinds of things we're trying to say here. But, you know, like this number, we're saying it's 2 more than a multiple of 3. Like later in the course, we'll say this number is 2 mod 3. It's congruent to 2 mod 3. We'll say this number is congruent to 1 mod 3. The language of congruences could have helped here, but that's coming down the line. Okay, so that's pretty much the end of our little puzzle. Do you have any questions on this? Okay, all right. I mean, just in the next couple of minutes, I'll just tell you what the next thing we're going to look at is without really doing anything very substantial. Maybe we'll just make a definition, possibly set some notation. But one of the next things we're going to look at is certain proofs of irrationality. So I'll just say a little bit. But that is talking about irrational numbers, numbers that are not rational. So let me just say a couple things about numbers that are rational, because that's the definition. You know, a real number, say R, this is called rational. If it can be written as a fraction, essentially. So by fraction, we mean fraction of integers. So if it can be written as R equals A over B, where A and B are integers. And of course, B is not 0. Okay, anything like this. Okay, so I mean, these are just sort of your traditional fractions with integer numerators and integer denominators. You know, I don't know that if I need to actually give you examples, but, you know, like a half, 9/7 or something. But, you know, anything you write like this sort of a thing. I guess I'll point out something like this counts, by the way. That counts, so does, you know, maybe this. And so those last 2 examples maybe are just notable because they are integers. So let me just point this fact out. Every integer is a rational number. So you can write it like that. Let me just share one fact with you that is probably something you heard of, but not something we'll prove. But, well, 2 facts, really. Okay, just about decimal expansions. So if you had a number presented in decimal form and it terminated somewhere, it's definitely rational. So let me just say that every terminating decimal is rational. There's an easy explanation for this, but this is a quick example. But if I had this number, and I mean exactly this number with no further digits, like it stopped perfectly right there, and everything that followed was zeros. This counts as, I mean, it is rational. Anything like this, you could just write it as, in this case, 78,514 divided by an appropriate power of 10, which is probably 1,000 in this case. Okay, so something like that. So that's lots of numbers then like that are rational. There's rational numbers everywhere. And I just wanted to share one more fact, which is that every number whose decimal expansion repeats let's say eventually repeats, so if you had a number like this, and the implication here is it's, you know, it's 5, 7, 5, 7, 5, 7, 5, 7, 5, 7, you know, like that. The thing that people would write like this, perhaps like 1.4 and then 5, 7 repeating, like in notation like that. Anyway, anytime you have something like this, it is in fact a rational number. You may have seen this argued before, but this actually classifies the rationals. They all have a number is rational if and only if it has a repeating decimal. This one counts as a repeating decimal where it's 0 repeating afterwards, if you want. But anyway, I mean, it may not be clear to you this is true. That's okay. I just am sharing it as a fact in case it slipped past you throughout your entire life. But I mean, don't ask where I got it, but it's true. So anyway, there's lots of rational numbers. They're everywhere. If you had some kind of real number where there was no pattern to the digits and they never repeated in any way, that would not be rational. That would be irrational. And so we'll just say that a real number that is not rational is called irrational. Okay, and so there are some famous examples like the square root of 2, for example, or the number pi, or the number e. These turn out to be irrational, okay, but how do you prove something like this? And we'll at least handle things like the square root of 2 in this class, and other radical numbers like that. Okay, that's where we'll go next. I mean, next, of course, is your exam, but then after that, when we return,